right, there we go. All right, so take a look at this question. This is one of the three posed at the end of class on Tuesday. This is something using the fundamental theorem of calculus. And just if you understand what the components of the expression are asking you for, you can come to an answer with only symbolic representations of the intermediate steps. I'll put up the other two questions we had as well. These kind of get increasingly challenging. The first one is like a medium level question. None of these have the answer of 0, like the first one we encountered on Tuesday. But the idea with all of these is, remember that the integral expression represents an accumulation. In these cases, this is a net accumulation from an input value of 2 up through a general value of x at the rate given by this integrand expression, this fraction. And so this expression in the integral, this m dx sort of expression, a rate used for an infinitesimal amount of time, we're adding up infinitely many of them over an interval. So we get a net accumulation between a starting and an ending point. Only since it's a general ending point, we get an accumulation formula, a net accumulation formula. And then we're looking for the derivative of that, the rate of change of this accumulation formula, which maybe you can see then. In this case, it's just with x as the endpoint from 2 through x, what's the rate at which we're accumulating? It's going to end up just being exactly the rate that you see inside with the letter x instead of the letter t. So meaning without actually trying to find an antiderivative for this expression, which it is possible, and you'll learn some about that actually in calculus too, how to find an antiderivative for that exactly. But in fact, you don't need to do that for this question. So if let me just name this. Let me call this, I'll call it g prime of t. I think I was using the R notation last time. But if this is g prime of t, and I want to know what happens between 2 and x, if I integrate this, well, if I think about, well, what accumulates at a rate g prime? Well, g accumulates. It would be g of x minus g of 2, according to the fundamental theorem of calculus. That covers this portion then, because as long as this is any derivative of g, or if g is any antiderivative of g prime, then what we have is true according to the fundamental theorem of calculus. And we only have one piece left to do, which is take the derivative of this net change expressed by subtracting the accumulation as opposed to adding the many bits of accumulation. So taking the derivative with respect to x of this, just two terms, derivative of g of x is g prime of x. And then the derivative of g of 2, which would be a number, subtracted from that would be 0. So g prime of x is all I need. And I named this inner part here g prime of t. So g prime of x would just have an x in that location. So eliminating the notation that we made up to finish this question should just be 7 over 25 plus x squared. So this next one's fairly similar. The difference, notice, is the other examples that were this medium level like this had the x at the top, meaning the end of the accumulation was the unknown point. Now we've got the beginning of the net accumulation being the unknown point or the variable point. So if we vary the beginning of the accumulation, you can see that, well, the expression here would just be somewhat reversed. The x would be in the second half and the number would be in the first half. But again, just, let me switch colors, ooh, something that'll show up here. If I call this, let's see, what's a good letter? R sub h of t. So that this is a rate of change function for something called h. As long as I can find anything that has this as a derivative, that's fine. And I don't actually need to find an antiderivative of this sine function. If you can imagine, say, oh, well, it must have been a cosine function or something, because the derivative of cosine, oh, derivative of cosine would be negative sine. So let me throw this on there. But if you try to come up with something like this, say, oh, well, it must have been this. Well, not quite, because if you take a derivative of this, there's chain rule. There'd be a times 6t. There's no 6t here. And if I say, oh, well, I can just do the divide by 6t like we did with some other stuff. Well, now it involves quotient rule. So there's not a simple way to kind of undo finding a derivative with this sort of expression. So don't worry about what its antiderivative is. We'll just express it symbolically as function h. And what we need, according to the fundamental theorem of calculus, is h of 7 minus h of x. And then we need to take a derivative with respect to x of that difference. And even though I don't have h of x written out, I know its derivative can be called r sub h of x, which would just be like this, but with an x in there. So I'm going to, let's see, where's my eraser? Get this out of the way. But that means I've got a derivative of 0 minus h prime of x, or r sub h of x. So it's after the subtraction sign. So the only difference between these two essentially is going to be like, oh, well, because of the difference in location of these x's, this ends up reversed. And that should make sense, because if we're thinking about varying x, and x is at the beginning of the interval, the rate at which we proceed from x is, well, depending on where it's farther or closer from x. And when x gets smaller, your interval gets larger. When x gets larger, your interval gets smaller, if you can imagine that. So that's why this negative sign here is talking about this rate. So in any case, to eliminate this made up notation, it'd just be 0 minus sine of 3x squared. Now, keep in mind, if this had been some other letter like q, and this, as long as this was also q, we could still do the problem. It would just be h of q here and ddq, and at the end we'd have a q. So it doesn't really, there's no need for this to be x. I was just using x as it's a fairly standard variable. Now, this is that most challenging type of question. This one involves using chain rule for derivatives on a general function, because of this, not just a variable, but a function of a variable on the integrand as our ending point for our accumulation. Granted, this is sort of a weird expression, thinking like, why would I do this? Well, also something you'll get to do a bit of in calculus too, putting weird expressions on the integral sign to express relative to something else where you're ending the accumulation, or where you're ending this net change. So again, just making up some letter or another. Let's say that I call this, let's see what would be a good name for this. Let's just use f. What if I call this f prime of w? Then I know that the integral part of this, according to the fundamental theorem of calculus, I would just need the ending point, f of cube root of x minus f of 1, and then take the derivative with respect to x to get the whole expression covered. So again, taking a derivative of f of not just x, but f of a whole function. If you want to think of this as f of g of x, and I'm taking a derivative of this, this is exactly what our chain rule says to do. The derivative of a composition of functions, I take the derivative of the outer function, leaving the inner part alone, and then multiply on, and it doesn't really matter the order I say and then, but it could be first, and multiply on the derivative of that inner function. You can work outside in or inside to out. But in the case of this, besides the fact that derivative of f of 1 is going to be 0 as usual, I need the derivative of, this is the challenging part, I need f prime evaluated at cube root of x, and then chain rule. So this is my f prime of g of x times g prime of x. So times the derivative of that cube root of x. So keeping in mind that cube root of x is the same as x to the 1/3, its derivative, found by power rule, is 1/3 x to the negative 2/3. So again, just final step to get rid of this made up notation here. F prime wasn't part of this. F prime of w is this expression. So f prime of cube root of x would be cube root of x over cube root of x minus 5. And then times this expression here, the derivative of cube root of x. Whatever format you want to put that in. We've kind of mixed rational powers and fractions here. That's fine. So final answer to this question would be that. There's a minus 0 that we don't have to write. But here's f prime of inner function, f prime of g of x times g prime of x. So I hope that you see that that's really just a use of chain rule, other than, it's, instead of being fully written out like questions on your derivative mastery test were, where I had like the cube root of x, sine of the cube root of x. It's just f of the cube root of x. But it's also not just like this with two generic functions, f of g. We have the inner function written out specifically and the outer function not, which is why this is a little bit strange seeming, but it is still just a utilization of chain rule. All right, so as I said, this was just kind of a practice at understanding what the fundamental theorem of calculus tells us. A lot of this is things that you'll use in part during later calculus courses in order to be able to understand how to express things more simply. But some of these, let me clear this off. This first integrand here and this third integrand here, you'll actually learn how to find the integral portion of that, find the antiderivatives of these rate functions directly without having to take a derivative to evaluate those. You'll learn that as a part of calculus 2. This one would involve some trig substitutions. Maybe you can see it's vaguely related to arctangent. If you remember the derivative of, let me write this down, arctangent of x is 1 over 1 plus x squared. This is that same sort of idea. It just takes a little bit of algebra to get it to look more like this. This expression, and again, this isn't something that you need to know for the final exam, but just thinking ahead, because I know you have to take 271 also, or whatever calculus 2, maybe it's 266, but whatever following calculus course you have to take, you're going to deal with how do you take antiderivatives, how do you integrate directly expressions like this. Well, this one uses a trick that we kind of did back in, we were proving product rule, I think. Add and subtract the same thing out of an expression. So w over w minus 5 is the same as w minus 5 over w minus 5 plus 5 over w minus 5, right? So by adding and subtracting a 5 out of this, I get something that's equivalent to 1 plus this, which, although this still isn't great, it's pretty close to a natural log expression. Maybe you can see we were talking about the derivative of 1 over x is, or the antiderivative of 1 over x involves a natural log. With this, it's just there's a chain rule, but it's the derivative of this denominator is just 1, so nothing fancy. This would be, the antiderivative of this would be natural log of w minus 5 in absolute values like we talked about before. Coefficient of 5, any derivative of 1 is an x or a w or whatever letter we're using. But not doing the antiderivatives, but just this expression itself can be rewritten in a different form so that it more closely resembles something we're used to. Same thing here, this 7 over 25 plus t squared. Now, if I factor out a 25 from the denominator, just to show you kind of what I mean by this, this would be the same. 25 plus, well, 25 multiplied onto t squared over 25. That's the same denominator there. And then the numerator of 7, it's like, oh, well, then this is just the same as 7 over 25 times 1 over 1 plus, and that's the format that we want, something squared. It's just not an x, but it's something squared. So it's just a chain rule away and a coefficient away from being an arctangent. So in any case, those are things coming up next semester. But let me get that out of the way. What I do want to talk about actually is some things that are a bit simpler than that, just some more basic instances of undoing chain rule. And we talked about a couple at the end of class on Tuesday, something like, what if I had an integral of, what was one that we did? Something like 5e to the 4t dt, meaning I need to find something that has this as its derivative. Well, if I take a derivative of 5e to the 4t, there's this times 4 from chain rule. If I want an antiderivative, I'm going to divide by 4 instead, just this simple numeric chain rule. That works out fine because that just leads to other numeric constant coefficients, which you don't have to do anything with their derivatives. There's no product or chain rule that suddenly gets put in place. And so we say things like this, like, oh, just a divide by 4 to compensate for the times 4 that happens if we were taking a derivative of this. So let's move on to talk about that a little bit. All right, I gotta get out of this one and find a different, let's see. No, I'm looking for Keynote. Sorry, I'm trying to get out of this Keynote and it doesn't want to let me. Hold on, let me unshare my screen entirely for a minute. This is being difficult. All right, let's see if I can get this back now. Ooh, there we go. Sorry, this is a little bit touchy with Keynote. All right, so undoing chain rule. We're also going to talk about some visual interpretations of integration. But chain rule, like we were just talking about, I think I had the F's and the G's written the other way around the last time, just because of the letters I already had. Doesn't really matter the letters. But if I have g of f of x, this is how chain rule works. So if I have an expression that I can see as a product where one of the two factors is the derivative of, or close enough to the derivative of, the inner portion of a composition that I can see, then I can think about undoing that chain rule. Now, this seems weird as a general premise. So our approach is going to be focus on finding the antiderivative of the exterior function. So like g prime to g. If you can see the other pieces somewhat match, maybe off by a coefficient or something, we can adjust for that later if that's easy enough to do. But let me show you what I mean. Look at this expression here. It's got two main factors to the integrand. I've got a simple factor, this x cubed, and a more complex factor, 8 plus x to the 4th raised to the 5th. So just ignoring this x cubed for a second, thinking about this messier portion, the longer portion of that. If I ask you to take a derivative of something with 8 plus x to the fourth all raised to a power, we'd say, oh, well, you do power rule and then times the derivative of the inside, which would be 4x cubed. So this isn't 4x cubed, it's x cubed, but there's some other numbers missing as well. But the powers of x are right, so that this, it looks like the end result of having done and simplified coefficients of chain rule. If this were to have been chain rule, I would have needed to have seen in the original something with a sixth power here. And then the derivative of the inside would involve like some other coefficient times x cubed. So this comes down to kind of a game of guess and check, although if you've done it a few times, you can make good guesses or just see what to do with the numbers kind of by pattern. But thinking about this, like, all right, well, let's just start with the antiderivative must have involved 8 plus x to the fourth raised to the sixth power. So what if it was just that? Is this the answer to our question? I mean, there could always be a constant, but is this our end result? Well, if I took a derivative of this, it would be 6 times 8 plus x to the fourth, all to the fifth power, and then times x cubed, or 4x cubed, rather. So it's almost right, but this on its own ends up with an extra numerical factor of 24 that this doesn't have. So guess how we compensate for that? There, that should do it, because if that, which would just carry through when we do the derivative, if that were there, that 1/24th, it would cancel out the 6 and the 4 factors, and we'd have precisely what we need. So our final answer, what's the antiderivative of this expression? 1/24th, 8 plus x to the fourth all raised to the sixth power. And then since this is a generic indefinite integral question, we add on the plus c to demonstrate the entire family of functions that all would have the same derivative. So this is not an easy process, but if you see this two factors, usually it's one big ugly factor and one simpler factor. If you can see this as two factors where one is at least vaguely related to, has the right powers of x to be the derivative of the inner piece of the messier composition looking part, we can probably do this work backwards through chain rule approach to find the antiderivative. All right, so let me pull up another question and I'll get some of this out of the way. So take a look at this one. Now this one's not written as a product, it's written as a quotient, but just as a starting point, realize we could write this as 3x to the fourth, and maybe useful for derivative purposes, saying, oh, times what, 7 minus 9x to the fifth, all to the negative half power. So if you can maybe see, it's somewhat similar to what we have above. We've got a different type of power. It was not written as a product originally, but take a minute. See if you can apply the same principle we did in the last question to come up with a derivative here. Or an antiderivative, rather. Thinking about chain rule. All right, so again, above we've got a sort of a simple factor and a compound factor, where the compound one, the inner portion of it, the inner portion of this composition of functions, its derivative is kind of like this. It's not the right coefficients, but a derivative of x to the fifth involves x to the fourth. The variables are right. So doing what we did before, this one was, oh, well, this was exterior-wise a fifth power function, so its antiderivative must have been a sixth power of the same thing. This one's a negative half power, so again, thinking the same way, 7 minus 9x to the fifth must have been to one higher power. And using the idea that we did last time, just, divided by a half, well, there we go, times 2. These two are reciprocals of one another, so that if I take the derivative of this, I end up with at least this part. There's no stray halves running around. But think about this. If I take the derivative of this as it is, so I'd copy down the 2. I'd do, let's see, 1/2 7 minus 9x to the fifth, all to the negative half power. That's supposed to be a fifth exponent. All times the derivative of the inside, which is negative, 45 x to the fourth. So those two are good. That makes a 1. All I've got that I don't want, I want to have a 3x to the fourth. And right now I have negative 45x to the fourth. So I just need to adjust this coefficient. I need it to be a 3. I don't need it to be a negative 45. So multiplying by 3 over negative 45 will accomplish that. And then I can simplify this. So I'll call that, and I'm sure that reduces to what? 1 and 15. So I'll call this negative 2/15 times, multiplying these two coefficients together is where I'm getting this negative 2/15 times 7 minus 9x to the fifth to the half power, otherwise known as negative 2/15 times the square root of 7 minus 9x to the fifth if you want. And again, if you check this, the 1/2 will cancel out that 2. The negative 9x to the fifth will give us a negative 45. That'll take care of the negative, and reduced by a factor of 15 will leave us with a 3 as desired. So it's not easy. And again, you'll do some things with this also in calculus too. This is a part of, this is the beginning part that they expect you will have seen the ideas of before in Calc 1, but not a lot of, but I'd say one component of the course from Calculus 1 that you're going to deal with in Calculus 2 is how do I find antiderivatives for more complex expressions, whether it involves just some algebra like we did last time, like, oh, let me make this look more like the derivative of arctangent, or trickery, how do I make this fraction a nicer sort of fraction, like a natural log 1 over sort of fraction instead of a w over, or this, how do I make the two factors of this relate to one another like the way that the two factors in chain rule are, by just adjusting coefficients. But you'll deal with some other things called trig substitution. Depending on what instructor you have and how much time you have, you might also talk about a technique called partial fractions, which you might have seen in an algebra class or a pre-calc class, also depending on what textbooks you used. But that gives you ways to break down rational expressions that are pretty ugly into simpler ones, like undoing fraction addition by separating out into different denominators. In any case, let's talk about some other things. All right, maybe. I don't want to go all the way through these, but just to kind of point out some similarities to the questions we just looked at. This top one here, just like question number 2 that we just did, it's not written as a product, but if you write it as a product, e to the 5x times e to the 5x oops, sorry, 5x plus 8 all to the negative 7th. You can say, oh yeah, here's the compound factor, its power function. This is approximately the derivative of the inside, just off by a factor of 5. So yep, we can think of that using undoing chain rule. Same thing here. Now in this case, it looks weird because unlike this example and the second one from the previous page, it's not the denominator that's the mess, but that's okay. We would have just this sign of square root of x plus 8. So here's the compound factor times x to the negative 1/2. And you can maybe see, oh yeah, this is approximately the derivative of this inside part. So there's various ways to help organize these, but if you can see one simpler factor as the derivative of an inner part of another factor, you're set to do this kind of undo chain rule. So focus on the big factor's antiderivative, which would be something about cosine. Cosine's derivative is negative sine, so negative cosine's derivative would be positive sine of the same thing. And then just figure out, well, this is the derivative of the inside, kind of what other numerical factors do I need to make it just right? Same thing here. All right, so what I want to talk about now is a little bit just kind of overview, review, and then also a different way to see this visually. So back at the start of the semester, this isn't quite how our rate function was lined up with our accumulation, but suppose I had an exact rate function, this red curve. I can approximate it by using constant rates of change for a little bit. Now we used the left method when we were going that direction. We used a method that's more kind of like this when we're going backwards from accumulation to approximating rate. But regardless, it's just picking the middle instead of the ends of the interval doesn't really make a difference in the end when you make the intervals infinitesimally small. But we took these approximate rates over small intervals, and each rate then contributes a bit to the accumulation. So at one interval in, we would have had accumulations, net accumulation here, starting at 0 and going up as much as is indicated by mdx over here using this first m. So our first rate times the width of the interval gives us a small amount of accumulation. And so when I go one interval to the right, I should have a small amount of accumulation, which is this height here, a part of what contributes to the full height by the time I'm at this, generically chosen, the slightly past 4. After I've done several intervals, I add all the pieces together, and each of these little pieces contributes to the overall height here. But those blue dots correspond to the heights that are delta x units apart along this accumulation function also. So the second rate gives us a little more, the third rate gives us a little more, and as we get more and more of these, they contribute to this accumulation over here. Now, another way to see this is visually. So looking at just the rate graph, ignoring the accumulation graph, which it's a geometric consequence of how we do our graphs, but you can do this when you're dealing with Cartesian XY graphing plane. But it's something that some people use. It's not necessarily useful, but it's good for sometimes visually estimating a numeric result for accumulation without having to draw the accumulation graph. So MDX for the first one, that gave us a little bit of accumulation that helped contribute to this entire amount here. But MDX also, with this height as our M or R1, and this width as dx, is also the area of this rectangle that whether I place the rectangle with its left end on the rate curve or like this was, it kind of fits underneath this shape here. So just thinking about this, like, oh, I've got positive rates, positive rates, positive rates, positive rates, but it's lower positive rates in the middle. And so if you want to estimate an amount of accumulation without drawing the accumulation graph, something you can do is think about, well, how much space is there under this rate graph? Because all that's really doing is talking about how high or how low or even negative the rate is. And so the space between the rate graph and the x-axis, if it's positive like this, that amount of area can tell us the amount of accumulation without having to draw the accumulation graph. So it's maybe helpful if you need a numeric estimate, if you're doing XY plane graphing, which most of the time we have in this class, but that's not always the case in other courses and other contexts, other content areas. Lots of times polar coordinates are used, and that does not work with this. But the area underneath also becomes more accurate, just like this accumulation estimate becomes more accurate if you use smaller intervals. And so in addition to using a visualization of that area underneath to estimate accumulation, if you want to, you could literally use this accumulation or use an integral to calculate exact area. So that might be useful in the cases of, let's say this is like a CAD design program, and this is the cross-sectional area of some sort of device. So I could measure how much space there is here by integrating this boundary curve. If it's a three-dimensional object, I could use that cross-sectional area to help me determine the volume of some sort of object. And that's something you're going to talk about also in calculus 2. There's a lot of this end of the class. You see, I keep saying, oh, well, you're going to do more with this next class. That's where we're going. I needed you to be ready for calculus 2 and all of the things that we've been working on, whether it's derivatives, whether it's chain rule, stuff like that, integration, visualizations, all of these things are things you're going to be continuing in your next class. So when I make smaller intervals here, in addition to getting me closer to an exact accumulation, if I want an exact accumulation, I use an integral. That exact accumulation can tell me, that integral can tell me exact accumulation. It can also tell me exact area. And this isn't like the goal of integration. It's just kind of a consequence of it. If that's what you need, if you need area, you can get it through integration. Like I said, it's sometimes useful for cross-sectional areas of computer design, things where you have a function that forms the boundary, or you can fit a function to the boundary of a shape and you need to know area for something that's not geometric, like circle, semicircle, ellipse, rectangle, triangle, shape under a whatever on earth this curve is, you can find using integrals if that's something that you need to do. So just to kind of sum up then, if f is a rate of change function, then the integral of f starting at a point A and going through x is a net accumulation, and we can draw that net accumulation. Now, if f is not necessarily something that I was thinking of as being a rate, but if I was literally just using its shape, then I can also think about the shape having an integral that represents the area underneath that shape. So thinking about that and some things we talked about earlier on, I think this, what were we talking about at the time? Oh, I know, we were finding derivatives of things that were parts of circles, and the derivative of a circle function ended up, or it was, what were we dealing with? Circle area function. We found the derivative of a circle area function, and it ended up being a circumference function, which is not a coincidence. It's actually related to this same principle here. Now that was something that's not a function, circles, but let me see if I can kind of sketch something quickly. So for instance, if I had just one quadrant worth of a circle. Let's say this is x squared plus, here I'll put it in regular format, x squared plus y squared equals r squared. But I'm only looking at x between 0 and r and only y between 0 and r. This is the equation of a circle with radius r, and this is 1/4 of it. So if I solve this for y, since this part fits the definition of function, it would be square root of r squared minus x squared. I'm not going to do the implicit differentiation. If I wanted to find the area of this quarter circle here, I could integrate this for any value of r from 0 to r. That's where we're interested in using this rate function, or this, whatever this shape defining this boundary function is. If I integrated this curve here, r squared, now you'd have to use a particular number here, from 0 to whatever value of r you want. So use the same value here for r as you do for there. This one's an r squared and just a regular r. This is a sort of expression that we wouldn't be talking about in this class. It's one of those, again, it needs some fancy calculus 2 stuff, but you'll talk about how to do that. Actually, it uses converting to polar coordinates. But if I pop this into GC, let me do that, you'll see that it comes up with, well, for whatever value of r, it'll be the area of a quarter of a circle with that radius. So let me pull up GC, and then we'll get back to this. GC. And let me share this with you. Oh, there we go. All right. So let's say that I use a value of, I'll just put it here, r equals 1. So I've defined my parameter value, and I want to integrate from 0 to 1, my square root of, let's see, r squared. Oh, actually I want this to be 0 to r, so I can change my parameter value. R squared plus x squared dx. And we said this should be a quarter of an area of a circle with radius 1. So area of a circle with radius 1 is, let's see, is it going to do it, or does it want, no, it's not doing it. It won't let me put in parameters here, I guess. There we go. Area of a circle, normally pi r squared. I guess I don't need to deal with this. I'll just have to type in individual values for r. So pi r squared with r equal to 1. If I have a quarter of a circle, there we go, 0.25 pi r squared. Oh, what is this doing? It's giving, I don't know why it's doing that. I did 0 to 1. Well, let me take a look at that later. I'm going to figure out what it's doing weirdly here, but I think it has to do with the fact that it doesn't like r's. If anyone else sees what it is right away, let me know. But that is a quarter of a circle with a radius of 1. I'm integrating that. Oh, I need a subtraction instead of addition. That's what it is. There we go. R squared minus x squared. Thank you. Me finally remembered what was going on here. So if I had a radius of 3, that would be this expression for the area, and versus this formula. You can see that that integral, using the boundary curve, properly modeled with a subtraction, not an addition, gives you the same exact results. Now this is, you'll see this looks a little bit different. Reason has to do with approximations that GC uses, not to do with the method. GC doesn't actually know how to find antiderivatives. What it's doing is literally finding an approximation by adding up not infinitely many, but a large number of different integrals. And the issue with a circle in particular, and why its area is going to be off in relatively few areas, in relatively few decimal places, has to do with right near that right-hand boundary. If you notice, that circle became vertical there, right? The tangent line at that right edge of the circle on the x-axis would be a vertical tangent line. And so approximations right near that boundary are going to be bad approximations, because no matter how small an interval you're going to use, it's not going to become infinite. You can't use an infinite value for your rate. So in any case, this is going to be, it's a little bit off, but you can see that it's calculating the same thing. And if I just change these to different, I need to change my limit of integration too. There we go. You can see it's the same. It's calculating the same things. It's just approximation with this integral using the MDX method versus using pi. Here, stuff that is an irrational expression with infinitely many decimal places, it's not going to be quite as accurate as, the integral is going to be quite as accurate as that. So in any case, let's go back to what we were talking about. Let me get Keynote back up again. Let's see, this guy. So if you can define the boundary curve, you can find the area under it by integrating. It works less well in approximation format when you have extremely close to vertical. So x cubed actually has the same issue. The function y equals x cubed right near the origin also has a vertical tangent line. Whenever you have those numerical approximations of the accumulation, so this with GC, as opposed to doing it directly using the fundamental theorem of calculus, there's going to be some numerical issues. And there are whole degrees you can get using like a whole series of 400 and 500 level courses on approximating solutions to various things, including integrals and algebra equations for which there aren't easy ways to find solutions. So in case you think like this is just a, oh, I'll figure this out next class, some yes, some no. But some of what you'll find out along the way is the sorts of problems for which there are lots of issues when trying to solve them, and things that why they don't work out very well, which is, it's a little bit disturbing to know that there are questions that are hard to solve no matter how much math you know, but it's also good to know that you can recognize the sorts of things that are going to have issues when you try to solve them. All right, so in any case then, let's take a look at then some questions related to, I think there's like 1 or 2 questions on the last homework assignment that involve areas as a way to apply derivatives derivatives and integrals to a visual sense. So this is function g of x. I have it written out in factored form just so you can see what the intercepts would be. Well, I guess it's shifted, so it's not quite. But in any case, this is just lovely cubic polynomial of some sort. It's nice and smooth, doesn't have any undefined derivatives, doesn't have any vertical spots to the curve, anything weird like that. But this curve is sometimes above the x-axis, sometimes below the x-axis, meaning if I were thinking of it as a rate, this rate has some positive values and some negative values. So accumulation that would occur due to it would sometimes be increasing and sometimes be decreasing. And we might, depending on, like looking left to right, things that you did on your last test. If this is a rate function, my rate is accumulating quickly, but then slowly or quickly goes to accumulating nothing right here. And then I'm deaccumulating. Whatever I amassed is now going away, and it's going away for a long time. My net accumulation, if I'm starting at this -0.5, is increasing through here, decreases all the way through whatever this is, 2.8, and that's a lot of decrease. And then it increases just a little at the end. Like I said, if you want to estimate net accumulation, one thing you can do is look at the space between the rate function and the x-axis. So I've got a little bit of accumulation modeled by this amount of space. And if you're just visually estimating, say, oh, that's kind of like a triangle. So how much did I accumulate? About 0.6 times 15 divided by 2, since it's a triangle. What is that? 9. So I've accumulated 9 between here and there. And then there's this whole negative stuff. I'm deaccumulating. I don't know, maybe you want to make another big triangle just to estimate this. So just using geometry, I can say, that's about 2.7 by 16, base and height of this triangle, and then divide by 2. And I have no idea what that is. 2.7 times 8 sounds like 30 something, but it's negative. So I accumulated, what I said, about 9, and then lost, by the time I'm to here, about 30, or whatever it comes out to be. Maybe half of that, 15? I don't know. In any case, I've lost a lot more than I gained during this first little bit, but then I gained some more at the end. So if you're trying to estimate net accumulation from negative 0.5 to wherever, I could look at the area under the curve. But keep in mind, this expression will give you net accumulation, so positives and negatives, right? So I'd have positive here, positive for this first section, negative from here, or if I stopped, if it's negative 0.5 through x, I'd have positive results up through here, maybe it'd end up being positive, maybe till about here, because by this point, the positive growth and the negative loss would about cancel one another out. And I continue going negative. So if I stopped my integral at any point up through here, I'd definitely have negative values, and maybe even through the end, it could still be negative overall. Not talking about trying to find an answer to this just yet, although we could pop it in GC and see, but just realize that this doesn't give me total area as in big positive number, bigger positive number, big positive number, and adding together. This gives me net accumulation. So all of this part in the middle, space-wise, is counted as negative, just like it should be. If I, thinking about the actual interpretation of this, this is a rate that's happening, and it's negative rates. It's taking away from what happened earlier. So this would give me most likely a slightly negative result, because the area underneath the x-axis, the area corresponding to where this rate is negative, seems to be more than the combined positive areas above the x-axis that I can see there. So just in terms of estimating net accumulation, you can kind of do that visually without having to draw the net accumulation function. So I'd have positive results for net accumulation in the red areas and negative results in the blue areas, because the rate is negative. So if I integrate all the way across, like I said, likely it's going to turn out to be slightly negative. You could pop this in GC and integrate it from -1/2 to 4 to see what the result is. But more important, you should see why it makes sense that it's probably slightly negative, because this area here, this amount of time spent at negative rates and how negative they are, is more than the time and the value of the positive rates. So you can call this net area. It's kind of a weird term, but if you want to talk about it as area, just net area or signed area are common ways to describe that, just because we're talking about this space, but not just how big it is, but where it is. And relative to the x-axis, because, well, if we're below the x-axis, in reality, what this is negative rates. And so there's things that are being caused to deaccumulate or decrease in their net value because of this being underneath here. So all of this is causing deaccumulation or reduction in a total amount, whereas these parts above are causing increases. So I can talk about this net area if I integrate like this. If I literally wanted to find how big these spaces are, regardless of where they are relative to the x-axis, we can do that too. We just have to be careful about it. So if I want to find the total area bounded by this graph G and the x-axis between -1/2 and 4, I can't do it in one shot because I've got 3 separate sections to the graph between -1/2 and this 0.1 something, whatever that is. I'm just going to call it x1. Between -1/2 and this point x1, whatever it is, I've got this positive amount of area. If I integrate this, I should expect to get a positive result. This center section I wrote with a negative sign in front. Now why that is because I know that if I integrate from x1 to this other intersection here, which looks to be about 2.8, if I integrate from here to there, I know I'm going to get something negative, right? Because throughout that interval, I'm de-accumulating. I've got negative rates throughout. So if I want to make it positive, I can throw a negative sign in front. In general, you could always just put an absolute value around a section to make sure that it comes out positive. But since I know that this is negative, if I integrate from x1 to x2, then by throwing a negative sign, I know I've made it positive. And then the third section, similar to the first, is a section where the rates are all positive. So integrating from x2 up through the given boundary of 4 should give a positive result, and therefore corresponds to the physical amount of space, that area. So if I add these 3 parts together, keeping this with a negative in front of it so that it looks like that, I get the total area. So it looks kind of strange that I can't just, oh, well, let me just integrate from end to end. What you get when you integrate from just straight across is net accumulation. If I want to know physical area, where I want negatives to be turned into positives, just to have an amount of space, then I have to put in the negative myself or reverse the sign on this whole section. So in terms of rates, that's not normally something we do. Like if I was talking about the populations increasing from the middle of last year through the beginning of this year, and then I expect it's going to be decreasing through 2.5 years from now and then increasing, there'd be no reason that I'd want to take the total number of people that left the city or whatever population I was talking about and change that into a positive number to add it on. That doesn't really make sense in terms of a rate. I think the only example I've ever thought of that has to do with this is maybe the difference between displacement and distance traveled. So if you were driving north for a while, then south for a while, and then north for a while at various speeds, so that the negative numbers indicate driving south and the positive numbers indicate driving north, if you just integrated straight through this from left to right, your result would tell you how far you are from where you started. But doing this would tell you how far you drove in each of those intervals. This is how far I drove north. This is how far I drove south. This is how far I drove north. And by putting this negative sign in front, it makes it into just a number of miles as opposed to being some negative number of miles that gets subtracted from your northward miles. So this putting a negative here actually makes this a positive expression. And so maybe I have like, whatever it was, 15 miles plus 30 miles plus 12 miles or something. And I add them all together. So that distance, total distance versus displacement. Displacement is just the literal change in position, not how you got there, but just the change in position from beginning to end. Versus distance driven would not care that this is in a different direction. It would just find the number of miles, find the number of miles, find the number of miles, add them all together. So in terms of what all of this is about. Um, there's a lot of times when I just said, you can pop this in GC. That's a fairly common sort of thing, not necessarily specific to using the program GC, but when we want to do computations, I want you to understand the underlying principle of what computations need to be done or how to set up an expression. But the grunt work sometimes of getting all the numbers just right, and certainly like getting down to the decimals, just like I don't want you to do long division with decimals manually. Lots of times, once you have expressions set up, we can let the computers take over from there. But what we really need you for is to do the setup. So in terms of that, and that's why the focus of this class was as it was, computers can do all of the procedures, whether it's even just things like finding derivatives and antiderivatives, far more quickly and without making mistakes than people can. So the only thing is that there has to be a user to the computer. You have to tell it what to do. So you need to be able to express what needs to happen accurately. And in the case of programming, also you need to be able to express it generally. So not just integrate this one particular function from 4 to 17, but maybe you have to set up, well, whatever the output was from my previous result, I need to put it as a starting point for my accumulation. And then the rate that I'm using afterward needs to be the integrand. And we're going to keep going until it gets to a point B, which B is going to be the input to something else. You need to be able to set up general expressions. So you need to understand not just a numerical result that you already have, but what sorts of things go into the expressions, what the pieces of the expressions represent for the functions you're putting together. Computers can't do that part. We need people to do that still. So we need you for that. And I know that if you've taken calculus classes before, this might have seemed different from what you did then, and even different from other non-calculus, like from other classes. I don't want you to think about this class as spending a lot of time on computation. Like I didn't just go through 3 examples of find area and get this number. I want you to just focus on how do you properly set up expressions to represent what you mean. So in terms of your studying for your final exam, which is Tuesday, 7 to 9 p.m., when you're going over questions, I don't want you to focus on like, let me solve this problem. I need some more problems to practice on. Think about what's the general process you use to start setting up, or how are the pieces of this expression related to one another? What's the meaning of the pieces? Because our final exam is multiple choice, just like the other 2 standard exams, or not the mastery. Although on the final, there's a couple of questions that are literally just, find a derivative or find an antiderivative. I think there's 2. So there are a couple of those, but those are the kind of boring questions. So there's not very many. But I want you to focus on, as you're studying, what's the purpose of setting this up? How does this relate to the rest of the class? The fundamental theorem of calculus really ties together all of the pieces that we're working on, other than just strictly the what are my derivative rules and how do I get an antiderivative out of this. So just summary wise, what this class was about, I hope that you don't just see it as a bunch of computations to do, but that you understand what the principles are, kind of extending from basic algebra principles of rate and rate of change to understand how we can use these basic constant rate of change relationships to extend well past that into modeling any situation where one thing depends on another, and that these are all the same ideas seen from different perspectives. So whether we started looking at a rate function and how we find accumulation from that, or once we had accumulation and we wanted to find rate, going back and forth, both of those can be seen without going through the computations, but just knowing that one should allow us to find the other. And if you know that you should be able to find it, and you know the relationship for how, like y, dy equals mdx, and y final is y initial plus mdx, that gets you a long way. Just those basic things that were part of Algebra 1 classes with different notation, but using them in more complex situations. So I hope that you see that all of what we've worked on the whole semester is interrelated, and it was just an exercise in looking at this from different perspectives. We had to introduce a lot of notation to be able to express this either accurately or precisely, or to be able to express how the estimations are done, because not only the exact answers are important, like I was talking about with the circle and the finding the area, in a lot of cases, you actually can't find an exact result using an initial method, and the best you can do is an approximation. So it's important to know, how can I set up an approximation to be good, and how good is this approximation going to be? That's a lot of what higher level math is about. Like, how do I set up to approximate this, and how far off is my result going to be? So this fundamental theorem of calculus, accumulation and net change, was our big overall piece. And I hope that you feel confident about this, so that when you're going on, not just to other math classes, but whatever your major is, you run across these same ideas there, thinking about, like you see something about how a population changes over time. You're like, ooh, I know how I could estimate, how much it's changed overall, or, lots of other things. You'll see some keywords, and I hope it reminds you of the sorts of things that we've been doing here. So this does take work. If you work hard to internalize these relationships between the various concepts we've worked on, as opposed to just thinking, I need to solve a particular question, you will be able to see this calculus and the patterns of it and the relationships in it in so many other classes, so many other sciences and math classes. Now, are you going to see it in literature class? Likely not. Spanish? Probably not. But in math and science, you will see this. They all, even biology, people say, oh, biology doesn't use much math. It does. It just takes you longer to get to that part of it. You will see it all over the place. And I hope that you keep thinking about those relationships. Keep them fresh in your mind. Your final exam, I'm going to say a couple other things, but your final exam is Tuesday, May 5th, 7 to 9. Just like exam 2, it's using the Respondus browser. So I didn't get any weird feedback other than, like I said, on Tuesday, a couple people had some slight internet lags. So there's like a couple freeze frames, but yeah, it seemed to go pretty well for everybody. We're going to use that method again for the final. I appreciate your patience and willingness to continue working during this weird semester that we've had, and I hope that you're staying healthy. Keep studying. But let me change us to Canvas. So in terms of studying in Canvas, this lecture will be in YouTube along with the rest of them. Look back through, I tried to put in descriptive, short but descriptive titles so you could kind of see what each lesson was about if you didn't have notes from a particular day or can't find where you put something. But in this summary module here, so lesson outlines from this week are up here, but other stuff, the review and the final, this is just a short description saying the exam is going to be in Respondus, and make sure you study. The final exam topics, this is, let's see, this will pop open here. Maybe. There we go. So this kind of breaks down the things to make sure you think about as you're studying, stuff related to our exam 1, constant rate of change, and starting from rate, measuring accumulation, our approximation sum that we dealt with, and the pieces of that, how you make an approximate rate function and use it. and interpreting graphs of rate functions. Then the exam two stuff, this should be fairly familiar because we just took exam two. And there's just a little bit extra. And some of this we talk, this is summary. So a lot of this is all built into what we've talked about throughout the class, but just things since your exam two that you might see more questions about that wouldn't have been on an earlier exam. This derivative of an integral, or finding antiderivatives. Just so like if you have a 1 over x, what's the antiderivative? Like, oh, natural log. So, something like that we hadn't really talked about doing problems like that prior to your exam two. But those last few and the area we talked about today, those are things that you might see questions about. You'll see some in the last homework assignments also. The derivative of an integral and the area stuff, that's all in the homework that's due tomorrow. You also have a quiz to work on over this weekend. It covers some of those same concepts and just kind of a couple problems. We tried to incorporate as many of the semester ideas into simple questions as possible. So it kind of is a little bit all-encompassing, but without being too long. It's 2 questions, but each one has a few different subparts to it. Don't forget to do that quiz. I put it due like just before the exam on purpose so that as a part of your review, you could be going over that, but you'll see the results to that prior to the exam. But this gives you an idea of what to study. If you want to try some problems, just so you're like exposed to the sorts of things. Again, these practice problems here, this isn't for any credit. It's just practice. There are 94 questions. Do as many or as few as you want. Work on them. If you have questions about them, those are good things to ask about at office hours. So just be ready for that. I don't have any additional office hours beyond today, but I will be around via email. Happy to chat with you if you want to schedule something with me individually. But I want you to focus on doing what you need to do. So I'm not going to schedule any events for us, but study, study, study. And on the 5th, just like with the exam two, I'll be around via email. So if something goes wrong, I'm sitting there watching and seeing who has and hasn't logged in, and if anybody has weird notifications popping up. So if you have a problem during the exam, email me. I will be monitoring my email that whole time and looking at your videos as soon as you are finished. And so if you finish at a weird time, like after 5 minutes, I'll know something went wrong and can help you get restarted. But I'm going to hang around for office hours now. That is it for our lectures for the semester. Thank you so much for, again, all your hard work. Study well, stay safe, and I will be in touch.